Hi everyone, Iregev here. So I want to devote 5 minutes to discuss this paper, Robust Adaptive Threshold for Control of False Alarms. It's basically, they describe two methods. One is the cell averaging CFAR detector that we all know from the radar domain. And the other one is the distribution-free detector. And they compare both to themselves in terms of performance. And second, they also compare it to what they call the clairvoyant detector, which we will see exactly what it is soon. So first they start with the distribution-free CFAR detection, and they say that, let's say we have a range profile for an FMCW radar. It's basically an IID distributed random variable x1 to xn. It's a vector, and let's say that we sort it by the order statistics x brackets sub brackets 1 to x sub bracket n. We can say something about this order statistics. If this vector is IID, then if we introduce the random variable c, which is defined as 1 minus f, capital F, of x, when we feed it the rth order statistic, where f, capital F, is the cumulative distribution function, the CDF, of the underlying random vector, then this C can be treated as the false alarm probability, PFA, and its PDF is given by this, which is a binomial random variable, which is interesting. Now we can use and calculate the expected value of this random variable C, or the expected value of the PFA that we will get. And this, as you can see, depending on the number of bins or measurements, and this R here, lowercase r, which is the order statistic. Okay, so if we set the threshold at, let's say, 30%, this R will be the 30 percentile, or the index that is corresponding to 30%. Okay, the threshold is what dictates the false alarm, and they show that the false alarm, the average false alarm, E of C, will be between PFA min and PFA max, that they describe here. And the threshold is given by this. The order statistics for a given PFA that we design is given by lowercase r, and lowercase r is also the order statistics or the threshold. Okay, so the algorithm they introduce is choose the PFA to design, form sample and an independent noise observation or noise plus signal, okay, that is approximately stationary. If PFA design is less than PFA mean, set to the PFA mean, okay, or sample more. And the last step implies that PFA design is greater or equal than PFA mean. Use 5 here, this equation, to set the threshold R, or XR. Okay, this detection region is the region to the right of the threshold. The associated PFA is given by 2, and again 2 is this expected value. Okay, so this will be the mean expected value. And there is then the cell averaging CFAR detector, which we all remember. And there is also what they call here a clairvoyant detector. What is that? Let's see. Distribution free. There it is. Clairvoyant detector, in which it's almost like CFAR, but we don't actually estimate the noise variance. We assume that we know it. And mathematically, we can prove that this is a uniformly most powerful detector of size PFA design. Okay, meaning that the clairvoyant detector is maximizing the detection probability while meeting the false alarm rate that we set. Okay, and these are the results for an exponentially distributed noise plus signal, swirling 1, I think. And you see these 3 lines, clairvoyant, CA, cell averaging detector, and distribution free detector, are almost by the same almost coincides, which means that they have almost the same performance. Thank you for listening, and if you want more information about the distribution free detector, feel free to email me or contact me through my website or join our Slack channel for Circuit of Knowledge. Thank you for listening.